Okay, so we've been talking about organic chemistry, obviously. Um, we got through sort of alkanes. We got into, where's that thing? There it is. Alkenes and alkynes. So remember that, we've talked about several classes of organic compounds. Our alkanes, which are basically our single bonded guys, super important, obviously, as you probably are seeing here in organic chemistry, as pretty much everybody kind of comes back to these alkanes, especially those first 10 names that we talked about. Really, really important. We also talked about alkenes, and alkenes. Ene has a double sounds good, double, but has a carbon double bond, and that is the functional group for an alkene. It has at least one. They also, as we've talked about, are based off of the alkane names. We do change the last part to ene instead of ane. um, Remember, we do a little bit different here with the numbering and so forth. When we number to name the alkenes, we want to give the double bond sort of the priority. So you want to number whichever way, again, gives your double bond the smaller number. All the other groups would be numbered accordingly and named in alphabetical order, like we've done before. We also talked about alkynes, YNES, and that is our triple bond functional group. And they also works kind of the same way. We want to give the priority to our triple bond in terms of numbering. Everybody else would be numbered the same way, groups that are attached at that point. We at the end, when we were all together, talked about isomers, specific isomers of cis or trans isomers. And cis or trans isomers are a result of really our double bonded carbon and some different groups, either on the same side of the double bond, which would be cis, or perhaps on opposite sides of the double bond, such as this, which obviously would be trans. um, so any questions on the stuff we talked about sort of last time here? Okay, so what we're going to do, since we're all back together here, is we're going to pick up with this part of the lecture. Those that have discussion today, I will go over the part where we kind of left off last time, through reactions of alkenes, I'll spit it out, through alkenes during discussion. And then we'll just kind of go forward here. So I know we were right in the middle when we were all together there of the cis trans naming one a few slides back. But if you have discussion tonight, we will go over that one and a few other slides after that. If you had discussion on Monday, we went through those slides on Monday during discussion. We ended up doing that. So I will just do that for those people that have discussion tonight. Okay, so picking up here with aromatic compounds. Aromatic compounds are basically compounds that consist of a benzene, and this is a special sort of compound that's basically 6 carbons, as we can see over here on the right. It also has 3 double bonds, so looks something like this. Again, at each of these points are a carbon, and there's also a hydrogen, which is not normally drawn at each of these points as well. So you can also draw a resonance structure for it, where we move the double bonds to the other side, like something like that. But even a lot of times, and in this book as well, you'll oftentimes see people draw the benzene ring with even a circle sort of in the middle. The circle represents really the double bonds that we see here, because they could be sort of in this arrangement, or they could be in that arrangement. Sometimes people will draw the circle there to represent that those electrons that make up the double bond are what are referred to as being delocalized. Basically, they can at any point sort of be moving around and stuff. So All three pictures are acceptable for drawing benzene. One looks like this, one that looks like up on the top there, or the circle should be fine. Anything that has a benzene in it is considered, again, an aromatic compound. And that's obviously the major part of the actual compound, obviously, is the benzene ring. So like when we normally look for the longest continuous carbon chain, clearly the benzene ring would be that in this particular case. And again, here are the different representations, and remembering that there are basically one hydrogen at each of them. And again, this guy right here is probably most of the time sort of the representation of benzene that you will see. When we go about naming compounds that contain benzene, there are a couple different ways that we name it. First off, there are some common names, sort of historical type names that are oftentimes still used today. And these are three examples of it here. This guy over here on the left is toluene. It's basically a benzene ring with a methyl group up on top. This is aniline, which is a benzene ring with a nitrogen containing group. This is an amine group attached. And this is phenol, which has basically an OH group, or like an alcohol group sort of attached to it. Now, we can name these sort of more simply, but these three names you should be familiar with. They do still pop up a lot in organic chemistry. So, somebody says phenol, this is what they're talking about. Somebody says aniline, this is what they're talking about. And obviously, if somebody says toluene, this is what it's talking about. And obviously, that is the straight line structure for toluene over there to the right. We could also sort of name this in a more sort of systematic way by basically just putting benzene at the end of the name. And basically, the group attached is methyl. So this could also be referred to as methylbenzene. And again, that's another way you could kind of name this, but you should be familiar definitely with these three guys, as even today they are historical type names that are still used very, very commonly in organic chemistry for these three guys that basically contain the benzene ring with these groups attached. Now, as you can see here, if we were going to sort of name these guys, if we have just really one group attached like we do here, which is our chlorine group, again, we just name it chlorobenzene. No need for a number, because again, it's assumed wherever that guy is located, that would be carbon number 1. In a case where we actually do have multiple groups attached, we do follow the same sort of procedure. We want to number the chain here, and this would be carbon 1 and carbon 2. Hence 1, 2, there are 2 chlorines, dichlorobenzene. Same thing here, this would be carbon 1 and carbon 3. Again, if we went the other way, we would have 1, 2, 3, 4, 5, too much. Bigger number, so 1, 3 dichlorobenzene, and obviously this is a 1, 4 dichlorobenzene. There's also another sort of way that we will name these, and explicitly sort of happens here with benzene, and that is these sort of positionings here. These positionings here of the, let me get a different color here. This sort of 1, 2 positioning of the groups doesn't have to be chlorines, but any groups. 1, 3 positioning of any groups on a benzene ring, or the 1, 4 positioning also has a historical type name. 1, 2 is the ortho positioning. 1,3 is the meta positioning. 1,4 is the para positioning. So sometimes people will use those names in benzene rings when you have groups at positions 1 and 2, 1 and 3, 1 and 4. And what they will use those names is basically not numbers. So what we would rename this if we kind of did the ortho naming is actually we just put an O for ortho dash dichloryl benzene. And when you see the O, you would recognize that it's ortho, and you would recognize that ortho means the 1,2 positioning. Same thing here would be M dichloryl benzene. Again, M meaning meta, meta meaning that you know that those groups are carbons 1 and 3. And lastly, as you could probably imagine, P is sometimes just used dichloryl benzene. And again, the P meaning obviously the para positioning, which would imply that those groups are sitting at 1 and 4. And again, although in this particular case, they were both chlorine groups, they do not have to be the same groups. It's just more the positioning is what ortho, meta, and para basically represent. And this is specifically also for a benzene ring aromatic compound is really the only place where we kind of use ortho, meta, and para sort of in the name. Those two you should know, the positioning of those guys, they also do pop up a good amount still in organic chemistry. Any questions on that there, the positionings? Now, because of those three that we talked about a little bit earlier that, you know, they sort of have that historical type name, when we have toluene, phenol, or aniline that has some type of substituent on it or some type of another group on it, the carbon that's attached to the methyl hydroxyl or amine group is carbon number 1. So what that means is if we look at the guy on the left there, do a little highlighting here, our main kind of longest carbon chain, if you will, is this entire benzene ring. And this part here is the aniline part of the name. And again, that's that special name that goes with it because that's sort of part of the big name. As you can see here, this carbon right here that has the NH2 group is carbon number 1. And then obviously we'd go 2 and 3 for our bromine. And that is how we get to the 3-bromol aniline in this particular case. Same thing here. If we look at this is our phenol, which is the big group here, which is all this part here. And that again is sort of where our base of our name comes from. In this particular case, the phenol actually has 2 other groups attached. We have a chlorine group and a bromine group. We got this guy and this guy. And numbering wise, if we went left to right, we end up with 2 and 4. If we actually went right to left, kind of clockwise, we would end up with 1, 2, 3, 4, 5, and 6. So 4 and 6 would be a larger number. So we would go counterclockwise here to get us the smaller number. Remember, when we're numbering it, pretty much is all about the smallest numbers, which we want. And that's how we get our number here for this guy to be 2 and this guy to be 4 alphabetical. The bromine comes first. So 4-bromol, 2-chlorophenol. Again, using this more historical name for the big part there. And then obviously at the end there, we have toluene, the guy right there in the middle. And coming down through here. And obviously in this particular case, we got 3 different groups attached, or 3 groups. I should say they're not all really different. 3 groups attached there. Here, numbering left to right or right to left, I think will yield you the same exact numbering. So you could go either way. Here we get 2 and 6 for our bromines. And that's where our 2,6-dibromol comes from. And then obviously our chlorine would be on carbon number 4. And obviously the base of our name would be the toluene. Any questions on those there? All right, so why don't you take a second here and figure out which one is the correct name here for both of these, and we'll talk about it. Okay, let's take a look here. So clearly we see a benzene ring. That's going to be our kind of, longest continuous carbon chain, which obviously would be sort of the base of the name, benzene. We have a Cl group there, or chlorine group. And again, because it's the only group attached on this ring, we don't need a number. So this should be chlorobenzene, which looks like B. Again, not necessary here because it's the only one attached, which means we assume that it is going to be carbon number 1. Any questions on that there? Looking at this answer is kind of an important thing. A reminder that if you see a 6-member ring such as this guy, that is cyclohexane, not benzene. There's no double bonds. If you see a 3-member ring with only 1 double bond, that is cyclohexene, also not benzene. It needs 3 double bonds for it to be benzene, or again, that kind of circle deal is basically benzene. So very common. People sometimes get these guys kind of confused. What's a benzene ring? What's the other one? So again, the other one, definitely not a benzene ring. Any questions on that there? All right, so if we take a look over here and kind of do a more traditional way of naming, which looks like is what they did there. Again, we got obviously our benzene ring here as our base. We have a methyl and a methyl group, so that is a dimethyl situation happening. Clearly, one of these need to be carbon 1. If we go clockwise, we end up with 1 and 3. Obviously, if we went the other way, 1, 2, 3, 4, 5, which is a larger number, so we would not want to go obviously in that direction. So that looks like a 1,3 dimethyl, and then put benzene at the end, and that looks like C is a winner here. This could also be 3-methyl toluene, right? Because that is toluene right there in the middle. So you could have used that more historical name like we just talked about, with this obviously being toluene, and then obviously 3-methyl toluene you could go with as well. Any questions on aromatic and how to name them there? Okay, so if I'm not mistaken, I believe that should wrap up this chapter. So give me one. Ethers, we have aldehydes, we have ketones, we have almost the rest of the organic lot, except for a few. So these are a lot of guys that contain oxygen. A lot of them contains sort of a carbon oxygen type bond. Alcohols here has an OH group. Thiols has a SH group. Ethers, carbon, oxygen, carbon. Aldehydes, carbon, oxygen, hydrogen double bond. And ketones, 3 carbons in a row with an oxygen double bond. So a lot of oxygen containing organic compounds here in this particular chapter. So let us get into this. Our functional groups here, which are important. Alcohols are the functional group. Remember, you do need to know what the functional group is for all these organic guys. So an alcohol is an OH group. Remember, the OH group is a polar group, more negative on the oxygen, more positive on the hydrogen. So when you see the OH group, that is a alcohol. Phenol, which we just saw, would basically fall into that. That's phenol, which we just saw. It has the OH group, makes it really a sort of like an alcohol, but it has the benzene ring, so it has its own sort of classification, which is a phenol. Thiol group, as I mentioned, has a sulfur containing group. An ether is a carbon, oxygen, carbon type group. That's what you need in terms of its run. And as we'll talk about later on, are Aldehydes and ketones have carbon oxygen double bonds kind of happening here. So looking at these functional groups, we again see our OH, our SH, and our carbon oxygen carbon is our functional group there. Now let's talk about how we go about naming alcohols. So naming alcohols is not too bad. Alcohols end in OL. So surprisingly enough, we drop the E off of the alkane and put OL on it. So, you know, if we had a 1 carbon alcohol, such as this, 1 carbon is based off of methane. Drop the E, has the OH group, makes it an alcohol. This is what we call methanol, OL. Same thing if we had 2 carbons here. We got carbon, carbon, OH. 2 carbons is based off of ethane. Drop the E. This becomes ethanol. We go to 3 carbons. With an OH group. Three carbons is based off of propane. Drop the E, this becomes propanol, OL. But in this particular case, much like what we do with our double bond or triple bond, when we get to about 3 or more carbons that have an alcohol on it, or an alcohol group, a functional group, we do have to give the location of where that OH group is at. And location, I mean carbon, and we would want to give it the smallest number for carbon. So carbon number 1 here, this is what is known as 1 propanol. The 1 is where the OH group is located. The reason we need to do that is we could take the same 3 carbons and lay up that OH group there on the 2nd carbon instead of the 1st. Still 3 carbons, still based off of propane, still dropping the E and doing the propanol, OL. But in this case, this is carbon 1 and carbon 2 and carbon 3. OH group is at carbon number 2. That is 2-propanol. So we give the OH group the number when we get to 3 or more carbons. And much like the double bond and triple bond, we want to make sure that the OH group ends up with the smallest number possible. So obviously in the top part here, we wouldn't want to call it like 1, 2, 3 propanol. We want to go with 1 propanol, 2 propanol here. Any questions on that there? Obviously, if there are other groups attached, you name them accordingly. Again, given the OH group the priority in terms of the numbering, everybody else would be numbered the same way. Any questions on that there? Now, just like if you remember, we talked about carbons and carbons being able to be classified as primary, secondary, or tertiary carbons, we could also classify alcohols as primary, secondary, or tertiary alcohols. Kind of works the same way. So for example, we'll go with the one I just drew there. Do this one here. So what we want to look at is the carbon that has the OH group attached to it. So that is the carbon that directly has the OH group attached to it. And basically what we want to look for is how many carbons are attached to that. So very simply, we see attached directly to that carbon is 1. which means this would be considered a primary alcohol. Now, if we had this situation here, let's draw a condensed formula here to save a little room. Again, if we sort of look at the carbon that has the OH group attached to it, that's that guy. And if we look how many carbons are directly attached to that guy, we see in this particular case, we have 1 carbon and 2 carbons. This would be what is referred to as a secondary alcohol. And lastly, if we had, we'll go here, we'll do a condensed formula to save some room. See this move. Let's just put an OH. There we go. If we look at this case here, the carbon that has the OH attached to it is this guy, and directly attached to that carbon is actually 3 other carbons. That is a 1, a 2, and a 3, and that would make it a tertiary alcohol. Any questions on that? So again, you could classify alcohols as primary, secondary, or tertiary. Really important, as we'll talk about a little later on this chapter, in terms of reactions. Depending on the type of alcohol it is, you could sort of predict the type of reaction it's going to go, whether it's a primary, secondary, or tertiary alcohol. Any questions on that there? All right, so why don't you take a second here, come up with the proper name here, and also while you're at it, come up with the classification. Is it a primary, secondary, or tertiary? So take a minute or two to see what you come up with. Okay, so we want to kind of follow our same approach. The deal is here, we're clearly going to still be looking for the longest continuous carbon chain. The difference is whenever we do this, we always want to make sure that the continuous longest carbon chain also contains the functional group as part of it. So in this case, we could clearly see the OH there, which means this is an alcohol, which means when we are counting it, if I could actually get something, there we go. We want to make sure that this longest continuous carbon chain, does have this sort of connected in with it. So this would be 1, 2, 3, 4, 5, 6, if I counted right there. You could also have gone where I started over here and went 1, 2, 3, 4, 5, and then went up to 6. And again, as we talked about, sometimes there's multiple ways to get the same result. So here I'm just going to take this straight one straight across so I could kind of see everything there. So clearly that is 6 carbons. So that is based off of hexane. We have an OH group, which tells us that this is now going to be hexanol, OL. We do want to number the chain to give the OH group the smallest number. And probably just looking at it, you can see if you went right to left here, that is going to give us the OH group with the smaller number. Then obviously if we went left to right, that would tell us then that this should be 2-hexanol, the 2 for the location of the OH group. And in this particular case, we still got one more thing hanging out in terms of a group, and that is our good friend, the methyl group over here. And because we locked into numbering this way, because the OH group gets the priority, we are locked into that methyl group being at carbon number 5. And that means it is 5-methyl dash 2-hexanol. Any questions on that name there? I put a line through it. Yeah. All right, let's try a couple more here. Why don't you go through here and name these guys? And while you're at it, why don't you also draw some here? So let's do, Let's do 3-methyl 2-butanol. Let's do how about 3-methyl cyclohexanol. And let's do one more here. Let's do we'll do the 2-propanol because I want to look at it again. All right, so guys on the right, why don't you draw them? Guys on the left there, why don't you name it? And while you're also at it, why don't you do the classification of each of these? Again, is it a primary, secondary, or tertiary alcohol? So take a couple minutes and see what you come up with. All right, let's take a look and see how we're doing on these. Again, we want to kind of follow our same normal procedure here. We want our longest continuous carbon chain. Clearly, in this case, again, since these are alcohols, we want to make sure our alcohols are obviously our OH groups are part of it. So looking over here at the first one, maybe, there we go. We could just go straight across here. 1, 2, 3, 4, 5. Again, we could also get 5 if we went down 4 and then up, but 5 looks like the longest. And obviously that does have the OH group attached to it. So clearly 5 there is based off of pentane. With the OH group, we now got pentanol. We want to give that guy, again, the smaller numbers. So again, just looking at it, we can see going right to left will achieve that. That's going to give us 2 pentanol. Here we got one more guy attached there, which is a methyl, which is now locked into that numbering as well. And that is now 4-methyl 2-pentanol. Any questions on that particular one there? Now, when we look at this guy here, again, as we talked about with those aromatics a second ago, we do got one of those kind of traditional guys there. Clearly, we got a benzene ring happening here. Could call it hydroxybenzene, but again, we got that OH group, and that is our phenol, right? That whole thing together is our phenol. That means that where the OH group is going to be carbon number 1. And we can see here, hopefully, if you go counterclockwise, that is going to give our bromine the smaller number. Obviously, if we went clockwise, we're going to end up with greater than 3. So this would be something like 3-bromol phenol here. Any question on those names? Now, we have some to draw here, so we'll start always when we're drawing just to work backwards. So working this way, first off, I see an OL, which tells me it's an alcohol, should have an OH group. The propane part tells me it is 3 carbons, and 2 tells me where the OH group is, which would be right there. Just like before here, we will fill in hydrogens to get us to 4 bonds. And there is our 2-propanol that we saw earlier. Question on that one. By the way, this is 2-propanol. Just so again, I think we may see it in a second, but things do have multiple type names. 2-propanol, this is also what is referred to as isopropyl alcohol. And that is because if you look right here, that is our isopropyl group that we talked about. And is also rubbing alcohol. So, the same organic guy can have multiple names, and it's very common that does occur. Working backwards here, I see the OL again, so it tells me alcohol. I see the butane type name there, tells me that is going to be 4 carbons in this case. 2-butanol tells me the OH group is at carbon number 2. And as we talked about previously, because you are drawing it, you could go left to right or right to left. I personally am going to go again here, left to right. So that's going to be carbon 1. That means that right there is carbon 2. And that takes care of that part of it. Because I went left to right, my carbon 3 would have to be here, which is where my methyl group should go. And now everything else will go hydrogens to get us to 4. That guy needs 3. Next carbon actually just needs 1. Next carbon also needs 1 carbon at the end there, needs 3. Any questions on that particular one there? Lastly, here we have cyclohexanol. So same idea, OL alcohol. Cyclohexanol, or it comes from cyclohexane, and that is our 6-member ring guy that's attached. To make it cyclohexanol, I need an OH group on it, and there is no number for that because wherever this guy is should be carbon number 1, which means if I go 2 and 3, that will be my methyl group. You can leave it actually as a line if you want, or you can write the methyl in, and that takes care of that. And that would be 3-methyl cyclohexanol. Any questions first off on the naming or the drawing of these alcohols? We also talked about doing some classification here, which I totally just went right over and forgot about. So let's go back and actually do that. If we look here at the first one, this is the carbon that has the OH group attached, and directly attached as 1 and 2 carbons. So this would be a secondary alcohol. This is the carbon right there. I put a red dot on it. That is the carbon that has the OH group. That means that that is a carbon that's attached right there. That also is a carbon that's attached right there. That would be a secondary alcohol as well. Over here, I guess, scribble a red mark on it there. That is the carbon that has the OH group. That was not what I was trying to do there. That is 1 carbon attached to it, 2 carbons. This guy also would be a secondary. Looks like we hit secondary on everything here. This guy is the carbon that has 1 and 2 attached to it. So another secondary. And lastly, here we hit secondaries on all of them, apparently. That is our carbon. So 1 carbon, 2 carbons, secondary. Again, they won't always be secondary. It just happens we ran a whole page here of secondary alcohols. Any questions on any of those things? Classification, naming, drawing of alcohols? Okay, so let's delve a little bit deeper into alcohols and a little bit of phenols. Ethanol, which is sometimes also referred to as ethyl alcohol, and that is because this is ethanol right here. And if you just take this part of it, that is the ethyl group, and that is the alcohol group. And that is why it's sometimes referred to as ethyl alcohol, just like when you have methanol. This is methanol. This is the methyl group, and also an alcohol, so sometimes referred to as methyl alcohol. So sometimes people will use those sort of names in addition to methanol or ethanol. Has been known, obviously, it is formed by the fermentation of sugars and grains. So we got some sugar here, goes through fermentation. We make some ethanol, some carbon dioxide, ethanol, all that good stuff there. Ethanol is produced by reacting ethene with water at high temperatures and pressures for commercial use. It's used as a solvent in perfumes, varnishes, medicine, and so forth. we basically can produce an alcohol by taking a guy like this, which is an alkene, and doing what is referred to as a hydration reaction, where basically what happens is, as we sort of talked about a little bit the other day, for some of you, I got too many hydrogens there. Take away a hydrogen. That's better. There we go. And we can think of water as H and OH. And what happens is this double bond becomes a single bond. And one hydrogen goes on from the water, and the OH comes on from the water as well. And we get an alcohol. So if you do a hydration reaction of an alkene, you produce a alcohol. Very often there, like we just saw. Also, there are sometimes a trihydroxy alcohol. Trihydroxy means that they're basically glycerin here has an OH group on all three carbons, hence the trihydroxy. It also has some polar groups and allows certain things to be attracted to water, and it's attracted to water through hydrogen bonding. Mine is positive, and obviously the OH group there can do the same thing, and we get some hydrogen bonding happening here. Ethylene glycol, which obviously, as you can see, has a couple of OHs, is basically antifreeze. We use antifreeze in our cars. Does a lot of things, including keeps our car from overboiling by raising the boiling point of the water in our car, in case you live in a really hot environment. Also keeps the water from freezing by lowering the freezing point of the water in your car. In case you live in a very, very cold environment. That way, when you get in your car, it starts and everything's not either frozen or over boiling or over hot. So ethylene glycol is the true name for what we commonly refer to as antifreeze. Obviously here, also we have some alcohols here with some phenols here. Really, here's our phenols part. And obviously you can see it's used to make some polycarbonated clear plastic that can be used for all kinds of things. Sometimes you can get this to sort of leach out, which is a problem sometimes. So sometimes they'll say, hey, is PBA free? So you don't have to worry about that. We're going to now talk about really reactions that alcohols undergo and the different types of reactions that they undergo. The first type of reaction is really the opposite of what we just talked about. So a hydration reaction is how we really make an alcohol. So first off, before we get to dehydration, the hydration reaction, which is basically where we add water in the form of HOH to an alkene, gets us a alcohol. So in every situation, the always important part of this reaction is always the carbon-carbon double bond. So when we add that water to it, double bond needs to become a single bond. At this point, each of these carbons are full. They cannot accept anything else. These are what is referred to as an addition reaction, which means they're going to both add in there. So to make room really for those guys coming in, we, as I mentioned earlier, make our double bond into a single bond. Now each of the carbons on the left-hand side and right-hand side, they both basically have room for something to attach. And basically water comes in as a hydrogen to one carbon, like this guy, and an OH to the other carbon here. and that is our water that's being added in there. So this is really the formation of an alcohol is done by adding water to an alkene. The opposite of that is that we will make an alkene through a process known as dehydration. So if we take an alcohol such as this one, we heat it up, which is heat, or sometimes referred to with like a little triangle there. This is an acid catalyst. And if we heat it up, we're going to basically remove water, and water is removed the exact same way that it is added. And what I mean by that is we remove a OH from one carbon, and then we remove an H from the other carbon. So OH from this carbon, H from the next carbon next to it. When that comes off, that is how we get our water back. What is left is this exact same thing without the water there. And when we remove the water, we got to put back the double bond. And again, that's how we get back to our alkene. Remember, to make the alcohol, we got rid of the double bond. So doing the opposite, removing the water, we have to put back the double bond. So they're really sort of opposites of each other. Now, if you had a sort of option, for example, and let me see if I can do this correctly. We're going to try this. So let's see here. Let's do. Let's do this. Do that. Let's do this. Let's do this. And let us do this. Okay. Now, if we were going to, I'll make my arrow go this way. We were going to heat this up and do a dehydration reaction of this. We're going to take out the water. Water is obviously going to come out as the OH. But in this particular case, there's actually two options as to where you could remove a hydrogen. We could take a hydrogen from the carbon to the left, but we could also take a hydrogen from the carbon to the right. Now, which one do you choose? Well, if you remember, and then half of you will remember later when we talk about it, but there is a rule when we do these unsymmetrical addition reactions, which is basically when we add hydrogen and something else like water, like bromine, like chlorine. The hydrogen always goes to the carbon that has the most hydrogens to begin with. When we remove the water, we actually remove it from the hydrogen, from the carbon that has the least number of hydrogens, which means we actually would want to remove this hydrogen and this OH, which means the double bond would actually go between the two, and we would end up with this. As our major product. So if you end up with a choice as to more than one option in terms of where you could remove the water part, you want to take it from the carbon that started with the least number of hydrogens when you're removing water in a dehydration reaction. Any questions on that there? Now, alcohols also go through oxidation and reduction reactions. And oxidation and reduction reactions always happen together. They're what are referred to as redox reactions, which I think we talked about earlier on when we talked about reactions a little bit. But there's basically some definitions of oxidation and reduction. Oxidation means that typically you have lost electrons. It also can mean that you have added oxygen from reactants to products. Also means that you could have lost hydrogen from reactants to products. So those are three definitions of oxidation: losing electrons, adding oxygen from left to right on the arrow, and losing hydrogen. Reduction has basically the opposite ones. Reduction means that you can gain electrons. You can lose oxygen from reactants to products. And lastly, you can gain H2 from reactants to products. In organic chemistry, pretty much we use these definitions: the losing and the gaining of oxygen and hydrogen as our definition of oxidation and reduction. In general chemistry, we look more at the sort of losing and gaining of electrons. So let's talk about alcohols and oxidation reactions that they undergo. First off, a primary alcohol will go through an oxidation reaction and it will produce what is referred to as an aldehyde. So let's talk about what is happening here. First off, this is our primary alcohol. That is our carbon that has one other carbon attached to it, making it our primary alcohol. An aldehyde has the functional group of carbon, oxygen, double bond, and a hydrogen. It is this last piece over here. So what is really happening here? Well, everything happens right at the carbon and the OH group. So grab that, there you go. So really everything is going to happen really at this carbon and where the OH group is and these guys. So this is really where all these sort of actions going to occur. When we go through oxidation here with a primary alcohol, the oxidation of a primary alcohol goes by the definition of removing H2 or losing H2. And where does the H2 come from? Well, it comes, one H always comes from the OH group. The other H comes from the carbon that's attached to the OH group. So what ends up happening is these two hydrogens come off as H2, and that leaves us a lonely carbon oxygen single bond, which then becomes a double bond. So when we lose those two hydrogens, we need to put a double bond between the carbon and the oxygen always. And this is what is known as a carbonyl carbon, this carbon oxygen double bond. And that's exactly what we see happen here if we go from left to right. Absolutely nothing changes other than we took an H from here and we took an H from there. Everything remains exactly the same. And we'll do a little highlighting to show you that. We'll go with a different color here. And let's go with this. So CH3 right here. CH3, exactly the same. We end up with carbon, hydrogen, and oxygen. Carbon, hydrogen, and oxygen. Again, we lost the two hydrogens that are circled, and we added in our double bond here because we lost the hydrogen. So the oxidation of a primary alcohol will result in an aldehyde. And when we have a primary alcohol, it could actually be further oxidized down the road to a carboxylic acid. And a carboxylic acid has this functional group. And it's this part right here. So what is the difference between this guy here and this guy? We added an oxygen right there, which again is another definition of oxidation. So the oxidation of a primary alcohol results in an aldehyde, and that's pretty much where you could lay it up. And if you continue on through that process of oxidation of a aldehyde, you will actually end up with a carboxylic acid. Now, what happens when we get to a secondary alcohol? So if we take a look at a secondary alcohol here, that is a carbon that's attached to one and two other carbons, and obviously has the OH group. So that is our secondary alcohol. Same thing happens here. We're going to lose two hydrogens, one from the OH group and one from the carbon. So if we look at this, that is the H from the OH group, that is the H from the carbon, and we're going to again turn that into a double bond as a result of that, which is what we see happen right here. Everything else remains the same. Again, if we look to the left here, carbon and three hydrogens, carbon and three hydrogens. We have our carbon and oxygen that becomes a double bond. And then we have a carbon and three hydrogens. So carbon and three hydrogens. When you oxidize a secondary alcohol, you do not get a aldehyde, but you get a ketone. The functional group of a ketone is three carbons in a row with a double bond in the middle. So that's a ketone. And that's what you see right here. Three carbons in a row with a double bond hanging out in the center. So primary alcohol, you get an aldehyde. When you oxidize it, secondary alcohol, you get a ketone. So of course we should talk about what happens with our tertiary alcohols. A tertiary alcohol does not go through oxidation. By the way, that is what the symbol right here means, oxidation. It does not go through oxidation because it wants to lose two hydrogens. The problem, though, is there is a hydrogen on the oxygen, no hydrogen directly attached to this carbon. So this carbon right here has no hydrogens attached, which is missing the problem of losing two hydrogens. So a tertiary alcohol will not go through any type of oxidation. So you will not get any type of oxidation occurring as a result of that. So you get basically no reaction. Any questions on that? So primary aldehyde oxidation, secondary ketone, tertiary nothing. Any questions on those there? Why don't we try some here just to see that as I got some stuff here. All right, let's say, why don't you write the product for each of these reactions here? So let me draw a few here and let you go after it. This would help if I draw it correctly, probably. All right. Let's do OH, H, and H. All right, So this guy goes through an oxidation. Let's see this guy in an oxidation. Let's do do let's do this guy as an oxidation. And let us do this guy. And let's do this guy. All right, take a couple of minutes here and draw up the products here of each of these reactions, see what you come up with. People get a little nervous drawing the products or reactions, but one thing you should always keep in mind is you essentially kind of have the picture in front of you. You just got to really focus in on really the only thing that sort of changes. So the first thing we'd want to do is really sort of analyze what we got going on here. We see an OH group, which tells us it's an alcohol. We might want to look at the carbon here and see it's attached to one other carbon, tells us it's a primary alcohol. And what that tells us is it's going to go through an oxidation, which means we're going to lose H2. And really the only part of this molecule that will change is in this region. This is really the only part really that does change. The way it changes is we're simply going to take off a hydrogen from the OH and a hydrogen from the carbon that's attached to the oxygen. Everything else is exactly the same. Nothing weird happens. So I see on the left there I have an H and a carbon and an H and an H. So I just copied everything here on the left. I still have a carbon and I still have an oxygen. And I removed my H2 that came off. Remember that what we do when we remove it, by the way, I still have a hydrogen over here. When we remove the carbon, the hydrogen from the carbon and the oxygen, we then need to put a double bond in there. And now we have our aldehyde right here. We went from ethanol, which is a alcohol, to ethanol, Al, which is an aldehyde. Put Al at the end of it, and it becomes an aldehyde name. Any question on that particular one there? Same thing if we look down on the bottom there in the middle, we have an alcohol. We again have a primary alcohol, as this is the only sort of carbon attached there. So once again, it's all about where the carbon oxygen is. Every single thing there, all of those things, which I'm now regretting writing, but all of those things basically stay the same. So I'll just copy from left to right here. And we got 1, 2, 3, 4, 5, 6. I lost count. 1, 2, 3, 4, 5, 6, 7, 8 hydrogen carbons, and the hydrogen is still there. Obviously, the hydrogens are all here. Hydrogen, 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 my carbon, oxygen. And remember, I took off this guy and this guy, which gave me H2. And that means that I then need to put a double bond in there, giving us our aldehyde here. Any questions on that one there? Again, nothing changes. Don't do anything weird. Just basically do what you need to do. Here we end up with a oxidation of a secondary alcohol. So this is a secondary alcohol, unlike this guy, which was a primary. Doesn't matter, it is the same deal. We're going to take the H from the O, H from the carbon, and again, we're going to double bond those guys. Everything else remains the same, so CH3, CH2, CH2, carbon, oxygen, and CH3, carbon, oxygen now becomes a double bond, and we have our H2 that came off. We went from a 1, 2, 3, 4, 5 pentanol to a ketone here, which is known as 1, 2, 3, 4, 5 pentanone, O-N-E, for a ketone, O-N-E, ketone, O-N-E, therefore our name of it. And this would be 2-pentanone, 2 for the location of the carbon-oxygen double bond. Any questions on either of those there? Same deal up here. We're going to go 1, 2, 3, 4, 5, 6 carbons. We have the OH group. It is a secondary alcohol here. So that means when it oxidizes, OH from the O, H from the carbon, everything else going to be the same. So CH3, CH2, carbon, oxygen now becomes a double bond. CH2, CH2, and CH3, and our H2 that comes off of it. Again, secondary alcohol up on top ends up at a ketone on the bottom. Any questions on that there? Lastly here, this is an alcohol that has 1, 2, 3 carbons attached. That's a tertiary alcohol that will not go through oxidation reaction because of the lack of hydrogen. So no hydrogen on that carbon, which means we cannot remove it and we cannot go through oxidation. Any questions on how to draw any of these reactions? By the way, in each of these cases that there was a reaction, you could go the opposite way and you could go this way. And this would be the reduction reaction, where we add an H there and an H there. That then makes that into a single bond and we get back the alcohol. Same thing here. If you went the other way, I'll just write it above, I guess, or whatever in there. That would be the reduction reaction. Same thing would happen. 2 H's, 1 H to there, 1 H to the carbon, just the way they came off. And you would get your primary alcohol back. And obviously, same thing here. Going the other way would be a reduction. 1 hydrogen to there, and 1 hydrogen to there. Double bond goes away and you get back your secondary alcohol, and exact same thing happens over here. 1 hydrogen to here, 1 hydrogen to there, and again that would take you back to your secondary alcohol. So every one of these oxidation reactions you basically can reverse by adding the H2 back in. It takes away the double bond at the carbon oxygen site, and it gives you back your alcohol. Any questions on that there? Okay. So obviously you do need to be able to write these products, know what you get when you oxidize a primary alcohol. You get an aldehyde. Oxidize a secondary alcohol, you get a ketone. Oxidize a tertiary alcohol, you get nothing because it cannot go through oxidation because of the missing hydrogen that is not present, I guess is the way to say that. A couple of things here about the alcohol. Methanol, also known as methyl alcohol, highly toxic, found in windshield washer fluid, paint stripper, and so forth. And again, here's our primary sort of alcohol, gets oxidized to formaldehyde, which is an aldehyde. And again, as we talked about, you could oxidize an aldehyde one more step to a carboxylic acid, which again is this part of the molecule, which is known as methanoic acid because it's a carboxylic acid. Ethanol, as we talked about, we can obviously test it to use a breathalyzer, which is what that person in the picture there is doing. And obviously we can metabolize alcohol depending on certain factors per hour. But same thing here. Here's our primary alcohol getting oxidized to our aldehyde, and our aldehyde getting oxidized to carbon dioxide and water in this particular reaction here. Any questions on alcohols here? All right, we will lay it up there. If you're off to lab, have a good lab and a good